Good afternoon, Professor Jones. My name is Nathan Eberhardt, and today I'm going to be presenting how sound is measured for my final project. So, two of the most common ways that sound is measured are decibels and hertz. So hertz is also referred to as pitch. It measures the frequency of sound. So I will demonstrate that momentarily on a piece of paper, what exactly frequency is. But to simply explain it, frequency is basically the wavelength of sound and how far apart each wave is for each interval of time. So here I've made a drawing in order to demonstrate how frequency works. So as you can see here, the top one, this is a lower frequency, which would lead to a lower pitch, which would lead to a lower hertz measurement, because as you can see, the wavelength is very long. It would be the whole paper. Here, you notice, and I apologize, my drawing skills are not that up to par. The wavelengths are much shorter, so as being this long, they are now this long. So, because this wavelength is shorter, the frequency is higher, the pitch is higher, so when measuring these with hertz, the hertz rating would be higher. So, that's all there is to say about that. Well, one final thing. Notice the amplitude of each of these, and I'm sorry, again, my drawing skills are not quite up to par. The amplitude is exactly the same. The intensity of the sound remains the same, while the frequency, the pitch, varies. So, amplitude has nothing to do with hertz, only frequency and wavelength has to do with hertz. Sounds that have a higher pitch, like this, tend to have a higher frequency, and sounds that have a lower pitch, like this, have a lower frequency. I'll show you this on my computer as well. I found a website that makes it very clear. A fun fact about hertz and frequency, humans can only hear pitches between 20 hertz and 20,000 hertz. Anything lower than that, the wavelength is too long and the pitch is too low. We cannot hear it. And anything above that, children tend to have more sensitive ears, so they can hear higher frequency sounds, and like dogs can hear that, like a dog whistle, you can't hear that. But anything above 20,000 hertz or somewhere around there, scientists have pretty much agreed on that 20,000 being the number. You can't hide just because the wavelength is too short, our ears are unable to perceive that sound. This right here is a website that I found that demonstrates how hertz work. So the website address is cisnowski.com/tone generator. I'm sorry, my computer is a bit messy. I've got a lot of fingerprints on the screen. But basically, you have this bar. You can slide it around and play different frequencies. I will demonstrate a few different sounds. So this is 20 hertz. And as you can see, there's nothing playing. My computer's at full volume, nothing. Now, we'll go 122 hertz. I'm not sure if you can hear that on the video, but I can just faintly hear a very low buzzing. It sounds almost like a bee. It's like a bzzz. Now I'll play something a little higher. 348 hertz. That you should be able to hear pretty clearly. It's very clearly audible, but it still has a very low pitch to it. I'll turn that up a little more. Now, we'll play something even higher. 1500 hertz. That has a much sharper tone to it, but you can hear that the pitch is much higher than the previous one. 3,844 hertz. Now this one is so high, this hurts my ears a little bit to listen to. We'll keep going. 9,000. So this one is much quieter than the previous frequency. So as I put this bar higher and higher, the wavelengths get shorter and shorter. They go like this and they get compressed. But the intensity remains the same. The amplitude of the sound is exactly the same. It's simply the frequency is getting higher and higher. 14,000. Again, even more high pitch. This one really starts to hurt the ears. 17,000. Now it's almost silent. I can barely hear it. 19,000. This is completely inaudible to me. I can't hear anything. 20,000. Nothing. So, that proves the general agreed upon 20 to 20,000 hertz being the human hearing capacity. So now that I've discussed hertz, which is used to measure the frequency and wavelength of sound, I will discuss decibels, which measures the amplitude of sound waves, also known as the intensity or volume of sounds that we hear. I have drawn up a little demonstration of how decibels and the amplitude of sounds work. So, with amplitude, frequency and wavelength do not matter at all. Amplitude is simply the intensity of the wave. It's how far from the top and the bottom of the wave, simply put. So, shorter amplitude, small amplitude will lead to a lesser volume. It's a less intense sound wave. And these are measured in decibels, which I will demonstrate shortly using my phone as a tool. So a sound with a higher amplitude would simply be a larger distance between the top and bottom of each wave. So this sound here, this sound wave, would be less intense and it would be quieter. This one is more intense, louder sound. So, in order to demonstrate sound amplitude and how decibels can be used to measure the amplitude of sound, I've gone to a few different places around our campus to demonstrate so. The first of those places that I have traveled to is my dorm, which did not involve much traveling to. I've been here working on my project all afternoon. So, a silent room would measure, well, let's see. I have this decibel meter downloaded on my computer. That will show. And just so you know, I researched this before. A regular conversation between two people, or in this case, me talking to this phone, is about 60 decibels. And you'll notice every time I speak, the decibel meter is peaking at 60 decibels, shown here. As you can see in my silent room, without me saying anything, there's nothing going on in here except for my roommate's fan running. The sound tends to sit around 8 to 10 decibels, which is relatively quiet. All right, so here I am in downtown Charleston, as you can see, at a very busy intersection. And I have whipped out my nifty decibel meter here. And we are getting a reading of about 70 decibels here at this busy intersection. So, as you can see, more stuff going on, more decibels. It's pretty cool. All right, so here I am at Marion Square in downtown Charleston. And once again, I've got the nifty decibel meter right here. What kind of numbers are we getting, Tommy?
Like 72.
So getting an average of 72 decibels here at Marion Square. So once again, it's a lot of stuff going on around us, which means a lot of sound going around us. All right. So, according to my scientific calculations, using my nifty decibel measuring device, these are the decibels present in our school's very own Liberty Fresh Foods cafeteria.
Why is it jumping up and down?
The noise levels are varying because we're conversating in the cafeteria. Thus, the decibels are varying. That's perfect. All right, check this out. We are now in a parking garage, as you can see. So these are the decibel measurements of the parking garage. What kind of numbers are we getting, Ty?
60s.
60s? Perfect. Boom. All right, so we have come to the Addleston Library, but we can't talk in there. We got to be quiet. Turn the camera around to show where we are. We're in the library. We're not supposed to be talking. All right, so that was it for my demonstration of decibels and hertz. I'd like to thank my friends Tommy and my roommate Tyree for the help with the project, and thank you, Professor Jones, for all the knowledge in physics in our many lectures. I will greatly appreciate that knowledge in physics too. So, thank you. Hope you enjoyed my presentation.